we're going to record this. All right, so we are ready to start, right? Everybody can hear me? Yvette, Dagny, we're good? Okay. We are going to start another technique for solving integrals today, which is pretty cool. So we have used other differentiating tricks like the power rule to solve integrals. Okay, we call it, I keep referring to it like the anti-power rule. Okay, we have also used effectively the chain rule to solve integrals, and that's U substitution that we were doing all this week. And now we're going to take basically the product rule and kind of do an anti-product rule to help us solve derivatives. Now remember, the whole point of any of these tricks that we have for solving derivatives is to make the derivative look simple enough or turn it into something simple enough so that you can look at it and go, oh, I know how to do this. Okay? So what we're trying to do is like uncover the easy, simple derivative that's hidden in there. Okay? So the one we're going to talk about today is called integration by parts or anti-differentiation by parts. Okay. And like I said, we use the power rule. So we're going to start by talking about some function that's going to be the product of two other functions. Okay, so u and v. And I'm going to take the derivatives of both sides with respect to x. Everything's a function of x. Okay? So I have dy dx, and that's really going to be d by dx of uv. So it could be, you know, x squared times cosine x or something. And then I'm going to use the product rule. Hey, sorry,
I'm just passing through.
I know, no problem. Okay, so when I use the power rule, I take my first thing times the derivative of my second thing plus the second thing times the derivative of the first thing. Okay? It looks a little weird, but you've done this. If it was x squared times cosine x, you could do it in a snap. Okay? I'm going to rearrange this just a little bit. Okay? Basically, I'm just going to bring this to the other side and rewrite it. So it's going to be u dv dx is going to be d by dx uv minus v times du dx. And then, everybody got written down with them up and down? Okay. Then, I'm going to integrate it all, okay? Which means that I need to have an integral symbol in a dx is equal to an integral symbol in a dx minus an integral symbol in a dx. And I'm going to fill in. So this is going to be u dv dx times d by dx uv times v du dx. My high school APCalc teacher used to use orange chalk when she did integrals, so I feel like I have to use orange sometimes. My homage to Mrs. Light. Okay. And then I'm kind of going to do some things here. So the antiderivative of the derivative u of uv is going to be u times v, right? Okay, I mean, like, that makes sense, the integral of the derivative. Okay. And then I can kind of sort of cancel these dx's. I'm sure there's like a really big calculus theory thing, and there's some theoretical math professor somewhere that's cringing, but we're just going to say that. So this is going to be du, and this side is going to be udv. Okay, which is the formula that you had from your book. So the way this works is that the integral of u dv is the thing you're given. Somebody says, here's an integral, solve it, and what you are being handed is an integral of u dv. You'll take part of it and you'll make it into a u, and you'll take part of it and you'll make it into a v, and then you do some things to it so that you can use this formula. Remember, the whole point here is to make the integral easier into something that you can integrate by looking at it. I would strongly suggest, as I have for other things, that the next 25 times you use integration by parts, you write down this formula. Do you remember how you messed up the quotient formula for taking a derivative? You put the negative in the wrong spot and you had factors mixed up. Many of you did. Not the same ones of you, but some of you are going to mess this up and forget what it is. Okay? So I firmly believe, based on over 20 years of teaching experience, that if you write it down a bunch of times, it will help you remember it. Okay? All right. So I think the best thing to do is an example so that you understand how this works. Okay? So the example you have is the integral of 2x plus 1 e to the x dx. So you come to an integral. What's the first thing you ask yourself? Can I solve it by inspection? Do I know what it is? Is it an inverse trig function? Can I use anti-power rule? Is it some trig function I recognize? Is it 1 over x? Is it e to the x? And the answer is no. What's the second thing you try? Use substitution. Okay, there might be some really easy thing lurking in there. Where do we look for u's? In parentheses, exponents, denominators, radicals, trig functions, e to the, that might be the exponent, things that are raised to exponents, okay? You could try, but if you let u be equal to x, because that's the exponent of e to the x, it's not going to simplify it for you. If you let u be equal to 2x plus 1, we still have to solve that for x and substitute in for e to the x anyway, so that's not really going to help. Okay? So the next tool that you have is integration by parts, which means you have to figure out what u is, and you have to figure out what dv is. So integration by parts, usually when you do this, you've got two functions that are multiplied by each other, okay? And one of those functions is going to go with the dx and going to be your dv. Okay? So remember, first of all, you're trying to simplify things, okay? And if you remember the formula, and let's write it down, u dv is going to be equal, the integral of u dv is going to be equal to uv times the integral of v du. Okay? Whatever I end up figuring out v to be, I have to be able to integrate it. I'd like it to be something simple. I'd like v to be nice and easy. One is a nice thing to integrate. Okay? So remember that you're trying to simplify. Number two, actually that was both things. You're trying to make things simpler, and you have to make sure that you can integrate whatever dv is. So I'm going to say that I'm going to let u be 2x plus 1. Because the formula says that I need to take the derivative of that. And what's the derivative of 2x plus 1? 2 times dx. Okay, but that's okay. I can integrate that. That is lovely. Okay? And that means that whatever's left, in this case, e to the x dx, is going to be my dv. And now I need to take the antiderivative of that. And what's the antiderivative of e to the x dx? E to the x. Okay. Usually a good choice for you is something that you're going to simplify. So something like a polynomial is a good choice. Okay. So my integral here is going to be equal to u times v. So that's going to be 2x plus 1 was u, e to the x was v. Minus, don't forget the minus sign, v, which in this case is e to the x, times du, which is 2 dx. My answer's wrong. Not this answer, but the answer I wrote in the book. We're in my notes. Okay, and then we just keep going. So I've got 2x plus 1 e to the x. I've come to an integral. I'm going to pull this 2 out. Do I know what the antiderivative of e to the x dx is? Yeah, what is it? It's just e to the x plus c. I can do a little simplifying here. I can distribute this e to the x. Okay, so that gives me 2x e to the x plus e to the x minus 2 e to the x plus c, or 2x e to the x minus e to the x plus c. Okay. How are you feeling? You want to try another one together, or you want to? Okay. Is there a checkpoint that we could go through together? Find my checkpoint answers. Anybody got a checkpoint they want to do? Fiona said 3.3. What else did I hear? Well, yeah, but they get harder as they go and teach you. Let's try 3.2. Okay, not that we won't do 3.3, Fiona, but that involves, and I'm going to tell you this, that involves doing integration by parts twice, which isn't a bad thing, but let's try to get integration by parts once first. Okay, so 3.2 is the integral of x natural log of x dx. Okay, so you've come to an integral. What's the first thing you ask yourself? Can you do it by inspection? Probably not. U substitution. Can we do a U substitution? No, the only thing I would substitute would be U equals X, and that's not going to make my life any easier. And remember, the goal of these tools is to make the integral simpler so that I can say, oh, I can do this by inspection. So that means we have to pick a U, and we have to pick a dv. And remember that whatever I make my dv, I have to be able to integrate it. So what do you think you might pick? Somebody pick a U for me.
Natural log of x.
Okay, you kind of have to let it be the natural log of x. But let's pretend for a minute that we're not as forward thinking as Katie. Okay? So let's say you're going to say, well, if I let u be equal to x, then du is dx, and that is simple. I can integrate that. Okay? But that means that dv is the natural log of x dx. Do you know how to integrate the natural log of x? What, Fiona?
It is x times to the natural log of x.
Okay, so you looked something up in the back of a book somewhere? It's what?
It's from the...
So you memorized something. Okay. So if you happen to have memorized this, you can do that. Okay. Or there's usually a whatchamacallit, integral table in the back of your book. You can use that. Just understand you may not have that on the AP exam. Okay. So maybe you know what that is, but I don't. Okay. So we're not going to do it that way. And from what Fiona is saying there, I'm not sure it's going to make things any easier. Okay, so it's probably just not a good choice. So sometimes you have to start again and flip it. So I'm going to say, as Katie suggested, that u is equal to the natural log of x, and dv is x dx. Now, omniscient narrator, I know that du is going to be equal to what? 1 over x dx, which is kind of sort of like a polynomial, right? So it might turn out to be okay. And what's v going to be? Okay, x squared over 2. And then I substitute in. And like I said, and I'm going to write it over here, I've got my formula, u dv is equal to uv minus the integral of v du. Worth writing down every time right now until we get our sea legs, as it were. So I have u times v, so that's going to give me 1/2 x squared natural log x minus the integral of v du, so that's x squared over 2 times 1 over x dx. Not too bad, right? Because I can combine my x squared and my 1 over x. So this becomes 1/2 x squared natural log of x minus, I've got a half out there, integral of x dx, right? So I've got 1/2 x squared natural log x minus 1/2, and what's the antiderivative of x dx? X squared over 2. Don't forget to add your plus c. Take a point off every time you forget to add plus c. So that gives us 1/2 x squared natural log of x minus x squared over 4 plus c. Okay. How about 3.4? Do we need to do 3.4? Deanna, we're going to save yours for Monday, okay? Because I think it's going to be scary. Okay. All right, so let's try checkpoint 3.4. So 3.4 is the integral from 0 to pi. That doesn't bother me. Of x cosine x dx. So again, I've come to an integral. What's the first thing you ask yourself? Can I solve it by inspection? Can I? Not really. How about u substitution? Can I do u substitution? Nope. My only option is really u equals x, and that's just going to be rewriting it. It's not going to make it simpler, which is our goal. So that leaves me with parts. Okay, and it's good. I got two things multiplied by each other, and I can go for it. So I've got to pick a u, and I have to pick a dv. Kim, what do you think?
U is cosine x?
Well, let's see what happens if we do that.
That feels like it's going to go badly.
And well, that's okay. Let's just see. Okay, because there's kind of a, it's kind of a, it's not really an art form, but there's an intuition that goes with this that you have to develop. Okay. So if u is equal to cosine x, then du is going to be what? Negative sine x dx. And if dv was x sine x, then v is going to be what? X squared over 2. Remember, my formula is the integral of u dv is equal to uv minus the integral of v du. Okay. Which means that I'm going to multiply these two things together and then take the integral. Is that simpler than what I started with? Yeah. Okay. So that might not have been the best choice. Let's try again. In general, not always, but in general, a good choice for you is the polynomial. And that's because if you take the derivative of a polynomial enough, eventually you will end up with a constant. Okay, so you might have to do more than one round of integration by parts, but eventually you're just going to end up with a constant, whatever it is. Trig functions, they never go away. They just keep cycling back and forth. Sine and cosine just keep alternating with some appropriate plus or minus sign in front. Okay? Same thing with e to the x. The derivative of e to the x is e to the x. The integral of e to the x is e to the x. That's just going to keep coming back. Okay? So if we let u be equal to x, then du is dx. And if dv is cosine x dx, v is going to be sine x. Okay. So we've got u times v, x sine x, minus my integral of v du, So that's sine x dx. Remember that this whole thing is being evaluated from 0 to pi over 2. Okay. That means that at the end, I'm going to have to take this constant, not this constant, I'm going to have to take that term out front and evaluate it between 0 and pi over 2 as well. Okay. So I'm going to have x sine x evaluated from 0 to pi over 2 minus, and what is the antiderivative of sine x dx? Or the antiderivative of negative sine x dx? Cosine. So this is going to give me plus cosine x. Again, we're going to evaluate it from 0 to pi over 2. Okay. And then I just have to remember to sub in. So this is going to give me pi over 2 times sine pi over 2 minus 0 times sine 0. Excuse me, that's my first term. Plus cosine pi over 2 minus cosine of 0. Which leaves me with pi over 2 minus 1. Right? Sine of pi over 2 is 1, sine of 0 is 0, cosine of pi over 2 is 0, cosine of 0 is 1. Okay? All right, you're not getting out of here without trying some on your own. Okay, so now we've done a bunch of examples. So you have in your notes some problems to try. So you try those. So I believe the first one. And try all 3 that are there. How are we doing with the first one here? We all right?
Wouldn't it be -4 e to the
Oh, yes. So there should be a 4 here. Yes, there should. Thank you. So,
I'm not sure. Would it comes up if you don't discriminate?
no, and I suppose, yes, she could have simplified that. But I didn't. If you did, yay for you. Okay? Other questions on this one? Remember, you don't have to write down what I do as long as you get to the same answer. So this is -4x equals -x.
Wait, why do you have a negative in the front of the 4x
Because it's v times v, and v has a negative sign in front of it.
Oh, okay.
Right?
Yeah.
Right? Like somebody, yeah. Because I'm perfectly capable of making that mistake. But I thought that. Okay, my Zoom friends, you doing all right there? Okay. All right, so we good with the first one? Again, you don't have to copy it down if you got it right. How we doing with this one? Okay, second one. Questions on this one? Okay. Let's solve it. How are we doing on the last one? Questions on this one? All right, we good? All right, let's try one more. I don't want to do, I want to skip, okay? Because I'd like to look at this one. The integral of x, secant squared x dx. Okay, which I think is just skip one and it's the next problem. Okay? So again, can you solve this by inspection? No. Can you solve this by u substitution? Probably not. So we've got integration by parts. So what are we going to let be u, and what are we going to let be dv?
U is equal to X.
Probably a good choice because you know what the antiderivative of secant squared is. And what's the antiderivative of secant squared? What? What? Tan x. Okay. And then what's du equal to? Dx. Okay. And remember our formula, u dv is equal to uv minus the integral of v du. You've probably written it down 5 times today, if not 6, and that is well into putting it into your memory. Okay, so our integral becomes u times v, so that's x tan x minus the integral of v du tan x dx. You've come to an integral. Can you solve it by inspection? Can you do a u substitution? Fiona says yes. Can you do it by parts? Not really. There's really only one thing. There's a couple times where you actually want to do it that way, but not here. So what are you going to do? Katie, you got it.
Well, I just have a question. So maybe, well, I thought I saw this on one of the textbooks, but why couldn't you do like tan squared x over 2?
Where would tan squared x over 2 come from?
Well, the anti-word, not never mind.
Okay. Fiona, what do you got for us?
Maybe you can change it into sine over cosine.
Yeah, sine x over cosine x. And now you've come to an integral. Can you solve it by inspection? Can you solve it using substitution? Where do we look for u's? In the denominator. What if, I'm going to let it be a w, so it's a w substitution because we already have a u. What if you let w be equal to cosine x? What would dw be equal to? Negative sine x dx. Do you have that? Yeah. Okay. So sometimes one technique isn't enough. You finish this, and we'll talk about it on Monday. Okay? Goodbye, my Zoom friends. Have a lovely weekend. Dagny, good luck. Oh, Dagny, you want to talk to me, don't you? But I am going to stop recording this.